Okay, we're back. So while we were away, what we did was we set up everybody in the class with speakers, and we did that out of convenience. If you're at home and you have an Arduino audio shield, and I can show you what that looks like if you like. What does an Arduino audio shield look like? Well, go to my DocJava website and go into my new store, and you can see the DSP audio shield is featured on Kickstarter, and there it is. The other thing you can find is images of the board. There's the board. There's the board. A board. We're bored of the board. And here's another picture of the board. Oh, wow. What is this? Oh, this must be, can you zoom out of these things? I guess not so easy. I don't know how to zoom out. That must be something people know how to do. Somebody not me. And then you can go to Amazon and you can get, here's one board. Oh, look, I sold out already. Holy mackerel. I gotta get back in there. Or you can buy two boards at a time. Two at once, and I made it so the minimum price is going to get you free shipping, because the new price on minimum from Amazon to get free shipping is $35. So I'm charging $35.01. That way you get it for free shipping. Or you can get an Arduino plus an Uno built in for only $38. Or you can get two boards in an Arduino Uno. Wow, only 8 left. So how exciting! Right? Very exciting. And you can pay with bitcoins. Nobody does that, by the way. Nobody. I mean, really, nobody. I'm not sure why. And I've got all this demo code with reverb and oscillators and everything. How exciting, right? So I think what would be really good is if we downloaded some of the Arduino code and then proceeded to use it in order to be able to make some sounds. Let's just see if we can find the on switch on the oscillator. So first thing you want to do is you want to get your code, and your question of course is going to be, how do I get the code? And the answer is, well, I get it from my Dropbox. How can I get it to you guys? If I download it, it comes right away. What I can do is I can share the link, and here's the link, and now I can take that link, copy it, and I could probably mail it to my Blackboard, right? So if I go to biomedical signal processing and send an email to all users, the subject will be audio, I don't know, audio Arduino shield code. That's a good subject. And I'll just say to sort of paste. And now he doesn't like to support cut and paste. This is astonishing to me. You can't do cut and paste with like, you know, why would anybody want an email where you can do cut and paste? So I'll hit submit, and now you all should get like a link with the zip file that you can just download that's being shared with you. Did you guys tell me if that's coming in now? You got it? See if that link allows you to do a download. Is that working? It is? Everybody getting this code? Mike? Checking your email? So anyways, once you get your code, it comes in a zip file, and I use 7-zip, and I extract it, and I guess I should move it someplace. It's got all this interesting stuff. So what I'll do is I'll cut it from here and I'll put it into a folder under the C drive. I have one called Lion. I don't know where I like to put these things, so I'll make a new looks like it's already in here. Paste. Yeah, it was already in there. Delete. Delete. And here it is. So that's what I got. There's my code. And I think what I'll do is I'll try this thing here called sign variable. So are you guys up to speed with me? Kevin, you with me? Okay. Mike, how about you? You're extracting now? So I'll just double click on sign variable, and if I double click on that, Arduino pops up, and I'll just hit go and see what happens. Uh-oh, COM3 can't be found. Here's COM4. I unplugged it and plugged it in again. Uploading. Oh, this is not good. I'm having trouble uploading. Done uploading. Yeah, I got an issue here with uploading. Programmer, serial port, board. I got everything done. Let's I'll unplug it, and then I'll plug it in again. Let's see what's going on here. I'll try and run it again. I think I had another AVR window open. Let's see if this works. Yeah, he's not able to download. Even the Blink program isn't downloading now. This is a classic problem with the I mean, he says COM4 is in there. Do I have to like reboot? Is that it? I really hate to... Is it working for you? It is. And it's faint that it's working? Kevin, how about you?
I can't get on the computer to download the thing.
Oh, you're having trouble downloading too? Well, here's what I'm thinking. I'm going to restart my Arduino program. I'm going to bring in my Blink program, and I'm going to see if I can get Blink to work. Yeah, I can't get this to work. Maybe if I change ports. Because this was fine before I unplugged it. Oh, now there's a COM3 port available. Ah! Now let's try an update. Yep. So when I switched the USB port, it found COM3 and then it was fine. So now if I go to my see if we can make this work properly. Because that's a showstopper, right? If you can't download it, you can't do anything. That was half volume. Now, these speakers without any power might actually work, but I don't know. Nope, they don't work at all. You gotta have power. That kind of makes sense. These are the speakers that come underneath the monitor. They need 12 volts. The other speaker that I have here, which is a powered speaker, you're welcome to try that if somebody needs more oomph from their little experiment. Let's see if that works. I'm going to try this powered speaker myself. I have a feeling it'll be fine. You can kind of see where having enough speakers for everybody makes a difference. Let's see if we got this working. Yeah, it works good. So if you're looking for, how you say, another speaker, something that's a little louder, I've got one here. And I'll just plug this one in here. And then let's turn that down. Okay. So I'm pretty happy with the fact that it's working now, thankfully. Whoops. I didn't like that phone anyway. So I thought what I'd do is kind of give you the guided tour to the code. Now, as you all know, or as you may know, and as fate would have it, Arduinos do not have DACs. A DAC is a digital to analog converter, and it can come in many flavors. A lot of times what happens is what you're trying to do is take a binary word and make a voltage, right? Very simple idea. Well, if you don't have a digital to analog converter, you can build one using a ladder of resistors known as the R2 ladder. What this will do is it'll take a digital word and it'll take the different bits and it'll weight the voltage for each bit by an integral power of 2 depending upon the position of the bit, just as though you were in what's known as positional notation. And that'll work good, but it takes a lot of space and it's not a particularly good DAC. Now another way you can do it is you could fabricate the R2 ladder in silicon. That's a lot of times what people do when they build DACs. Sometimes they even trim the lasers with trim the resistors with lasers, and these are called laser trim DACs, and they can give you very good accuracy. Analog Devices, a company based in Massachusetts, used to make laser trim DACs that we used. There's another way to do this, very fast. DAC is called an op-amp based DAC, right? And that'll give you some reasonably good results. But what we have here is something a little bit different. We're using what's known as pulse width modulation. And pulse width modulation, what it does is it takes a fast square wave and changes the amount of time that the square wave is up. That is, it changes the duty cycle of the square wave. With precision in your ability to change the duty cycle of the square wave, you can take the output from the square wave generator and put it into a capacitor. The capacitor then integrates the square wave and makes a voltage. And so in effect, what you're doing is you're making a DAC using what's known as direct digital synthesis, or DDS. It's a basic signal processing technique. People do this all the time. You don't need an Arduino for this, okay? Your basic idea here is all you're going to do is modulate the duty cycle. Duty cycle is generally defined as the percentage of the time in which something is on versus the amount of time in which it is off. So a 50% duty cycle means it's on 50% of the time and off 50% of the time. Similarly, an 80% duty cycle means it's on 80% of the time and off 20% of the time. That's simple enough, right? So if you can vary the duty cycle with precision, then you can have a very precise DAC. They call this a PWM type DAC. Now when you go through this code, you'll see there's an awful lot of extra stuff being added that detects whether or not you're on a Leonardo or an Uno, or an ATmega328P, or an ATmega32U4. And the reason you do that is because there are specific registers on each of these chips which can be used to modulate the duty cycle of the DAC. So if you're going to build a PWM DAC, you've got to deal with the fact that adjusting the duty cycle on that DAC is very CPU specific, because each timer and its register locations are different depending upon which model of Arduino you're in. And that's kind of a pain, and it makes your code very non-portable. And that's a problem. There are certain, I'll call them artifacts, which are not object-oriented. For example, the define that we have over in here, where we're putting in constants, these get substituted, these constants, at compile time. So when it says is Uno is 0, is Uno is 1, if you change that from a 1 to a 0 and you change Leonardo to a 1, then you'll have different pieces of code expanded by the compiler. So if you decide to plug this into a Leonardo instead of an Uno, you've got to edit this code. It doesn't automatically detect anything. And so that's a big deal for some people. There's this little bit in here called clear bit and set bit, and this will set bit and clear bit I, and you can go into a specific register and then you can proceed to clear the bit or set the bit. Let's see now, what else do we have? This is an A to D converter, ADC0, and here's another one, ADC1. One of these ADCs is used to read in the variable resistor, and the other one is used to read in the audio. So two different ADCs are needed for the two different things. The resistor is completely, the variable resistor is completely programmable. So it doesn't have to use, you say, oh, I look at it and I think, it's a volume control. But it's not, right? Because when you listen to the audio output and then you turn the volume control, what do you hear? Right? It's changing frequency. So it's not changing volume at all. In fact, you can program it to do whatever you like. And so that's one of those things where you might like to have an opportunity to change something like the amount of delay, or the number of reverb recycles, or in our case, where exactly you'd like to set the threshold on an FFT for doing noise reduction. Ooh, right? Because if you remember, we were playing an awful lot of fun games with our FFTs when attempting to do FFT-based noise reduction, and part of it was coming up with the threshold needed for the power spectral density for the noise that we wanted to squelch. So if that was a squelch control for your FFT, how cool would that be? Right? Huh? Huh? Hmm? Huh? Okay. So then when you look at pin modes output, that's just what it says. You look at some of these pins here and you can kind of see them. If you stare down at your audio shield, from the top, you'll see there is a pin 9, and if you look real carefully at pin 9, you'll see there's a trace that goes right over to one of the resistors, and I believe it says R5. So if you can see R5, the other end of it is connected to an inductor, and I think it's called L1. That's the large inductor with the 3 orange bands and the gold band on it. So R9 with the inductor, that's your audio output. So if you could follow along with me, take a look at pin 9, follow the trace. It goes through a resistor, R5, then follow the other end of R5, and it goes into an inductor, L1, then follow the other end of the inductor, L1, and it goes into a bypass capacitor that says 10 nanofarads, and that's accurate and correct. And then if you follow the other end of the 10 nanofarad capacitor, you'll see it says audio output. So there's your implementation of your pulse width modulation DAC, right? It's a resistor and a capacitor and a inductor. It's a filter. It's a low pass filter built with a resistor and an inductor and a capacitor. From a mechanical engineer's point of view, it has the differential equation that's the same as your shock absorber, right? Because what it's doing is it's taking the bumps out of the road and essentially turning that energy into heat, but instead of letting it oscillate wildly, there's a damper in there. And the damper is usually an oil-filled shock, right, with hydraulic fluid in it. So that's essentially the mechanical equivalent of your shock absorber on the output, giving you your pulse width modulation. So then the next part, this is the application-specific part, fill the sine wave. And what this does is it lets you take an arbitrary trigonometric function, in my case a sine wave, create a wave table, and put that into memory. So remember we talked about ways in which you could speed an FFT. One thing you can do is you can make up a table. Once you have a table, you don't have to keep computing things like sine and cosine. You can pre-compute the whole thing. Let's take a look at that fill the sine wave, and we'll ignore some of the bit flipping we're doing here on the multiplexers and the timer counters. Now somewhere in here it says fill the sine wave. And here it is. Now I'd like to get rid of my console on the bottom, but apparently that is not easy. You can go up, but you can't go down. Is that it? I'd like to make that disappear, but I don't know how. Too bad. Okay, life in a big city. So here's my change in x, dx, which is 2 pi divided by 512. Where'd the 512 come from? Well, there's 512 elements in my byte array, in my buffer. And what I'd like to do is I'd like to go through each one of the 512 elements, and I'd like to fill them. So I create this little index right in through here. I bias it by 127. And when you look at it and you go, why is he doing that? I have to think it's because I want a number that goes from 0 to 256. dd of IW. What's IW? IW is the index of the waveform. BB, where's BB being set? Oh, right here. BB is FD plus 127. Cosine, that should probably go from I wonder if there's a separate cosine function in here somewhere. No, it's the standard cosine function. Normally cosine is done so that it goes from -1 to plus 1. And I'm thinking that's the case here. What you can do, if you have any doubts, is serial.println. Isn't that how it works? Println? Quote FD equals end quote end paren sem. I'm not sure if that's right. When I go from one language to another, sometimes it confuses me. But that looks like it's right. Serial.println. Oh, I know what's wrong. This doesn't need the print line. I think you can just do a print without a print line. And then put out FD. So now you can actually see the values as the wavetable is constructed. Let's see if that's true. Control-Shift-M should bring up the monitor. It says it's uploading. Oh, I got an error again. Did anybody else get an error?
Did you put cosigners in the code, or was that?
It was already there.
Does that have 127 times sine?
Oh, really?
Yeah.
Does everybody have 127 times sine? I'm having issues with the serial port here. He can't seem to upload. I'm very weirded out by that. I think I have to switch my serial port again. I don't get that. But you know, sometimes what happens is these things need an extra power supply and you don't get enough power from the laptop. And if that's the case, then I should probably just bring in a bunch of AC adapters. What a pain, right? Serial port COM3 and upload using programmer. Uploading. Done uploading. See, now that time it worked fine. Control-Shift-M. Okay, now that just spit out a whole ton of crap. But it looks like it's the wrong baud rate. I set the baud rate in here, and I believe it was set to something high speed. Yeah, that says 56,600. So if you need to reset your baud rate, serial monitor 56,600. And now it's coming out. And that's great. And you can see why you have to add 127, because it's going to plus minus 128. So you say that was sine in your code, but cosine in mine? Let's put the sine back in. Yeah, seems alright. Yeah, it seems to be working. Now the question in my mind is, how come sine is coming out with a number that's so much higher than 1? Oh, because it's being multiplied by 127. Silly me. Right? So if sine is varying from -1 to +1, then sine times 127 is varying from -127 to +127. And so it makes perfect sense that you should add 127 before you set to dd. Now when you take a look at what dd is, right, that's supposed to be your wavetable. Let's see if we can find it real quick. And there it is, it's byte. So by setting the wavetable to byte, you get an opportunity now to save a whole bunch of memory, because this is fixed point values coming in off of your sine wave. And it's giving you, 8 bits of dynamic range only. But that's fair. So now here is what I would call an opportunity to change the code a little bit. Suppose you said you wanted to take sine and add to it something else, like 0.5 times the same thing, sine, but at a different frequency, 2 times FCNT. Then multiply that by this sine wave, and that should give you some interesting harmonics. So now you're doing what I would call constructive synthesis. And he says he's done uploading. Let's see what happens. So now it doesn't sound like a pure sine tone anymore. And you can hear the harmonics in there, right? So that's kind of cool. What else can you do? Well, when you look at how you generate sine waves and cosine waves and things like this, you get a sense of a kind of synthesis which I like to call constructive synthesis, where constructive synthesis uses the principle of superposition. And what you can do here is you can add all of the odd harmonics, for example, and let's see, we'll put this in the third harmonic, and then we'll do it again, and we will add it, paste, plus, and then we'll put in the fifth harmonic, and see how that works. So in fact, what happens when you add up all of the odd harmonics, and you can actually Google this one, you start to get square waves. Adding all the odd harmonics. And so here is a way in which you can formulate the Taylor series approximation to the square wave. And you can take all the odd harmonics and you can keep adding them up until you get something that's closer and closer to the square wave. And there are other kinds of waveforms you can do as well. You could add all the even harmonics. I think you get a triangle wave. Oops. Oh, he's not telling me here, but I can just do it. Right, because to get the even harmonics, I can do 2 and then 4. See how that works. Well, it's very annoying. So what do you think of that? Slick, right? Have you guys tried any of the other stuff in the folder yet? Not yet? Let's see what we can do to bring up some other stuff. It's fun, right? Very fun. Here's one called Song Out. Not exactly sure how that's going to work. Let's see if this will work. Okay. Right. So now with this, it's generating square waves straight out the top without using the direct digital synthesis. And these notes represent what I would call a major scale. So this is A sharp, B, C, C sharp, D, D sharp, E. Then this would be up an octave with A. And so now you can get an opportunity to play major scales. Fun, isn't it? No? Yes. Very fun. In fact, if you think about it, if you have a monophonic instrument coming in, like a flute, you should be able to do pitch detection with your FFT and then create a tone that sort of mirrors what the flute tone is. So in a sense, what you're doing is you're taking one instrument and turning it into a different instrument. How cool, right? Your Korg guitar tuner might actually be able to do a reasonable job of pitch detection, but here now you can do it with your Arduino and turn it into a synthesizer. Eh? 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 It's annoying. People shouldn't do that. Something tells me that really it bothers people. But it doesn't stop me. So then I've got a few other things in here which are really targeting what I would call audio processing. But in order to do audio processing with an ADD converter on a microcontroller, you have to give the ADD converter something to bite on. The ADD converter in this microcontroller wants to see a signal that varies between 0 and 5 volts. Okay. Does anybody know the amplitude of a microphone signal? It's not 0 to 5 volts. Okay. It's more like 0 to 10 millivolts. So if you think about it, if you have an ADD converter and the ADD converter wants 0 to 5 volts and it's an 8-bit ADD converter, what is the minimum voltage that it can detect? Well, let's break out our calculator. Okay. 5 volts divided by 2 to the 8, which is 256, is equal to 0.19 volts. So if I multiply that by 1,000 to get millivolts, then the minimum voltage that the ADD converter can detect is 19 millivolts. So what that means to me, the originator of microphone signals that go from 0 to 10 millivolts, 0 to 10 millivolts, is it's generating nothing that the ADD converter can detect. Really, nothing. So what that means to you is that if you take this desktop microphone and plug it straight into the ADD converter without a proper mic preamp, you will hear bupkis. Nothing, nada, zilch, right? Because 10 millivolts is not 5 volts, and it's not even close. It's off by orders of magnitude, right? I mean, how many orders of magnitude? You're looking for a number in here that's like 5,000. So to get 5,000 out of 19, you're off by 2 orders of magnitude. So you need a 100 times gain from a microphone preamp before the analog audio input is going to be able to give you anything, right? So how does one do that? How can you do that? How could we possibly do that? Well, you all have how you say laptops? Do you have laptops? Well, the laptops have microphones. Did you know that, right? And the microphones can play directly through the speaker. You see? So if what you do on your laptop is you make it so that you're listening to the microphone and you play it through directly to the speaker, you can take the output from your laptop, the headphone output, and plug it straight into the Arduino Uno. Slick, right? So what does that mean to me? The person who's recording from the microphone right now, well, what it means is if it starts to play directly from the laptop into the laptop speaker, I'll start to hear feedback. And that's probably true, right? So we can do that as an experiment. It's typically done within the control panel. You need to get to the sound area, which is in here somewhere. So there it is. And then there's something or other about setting up microphone properties. Now, check it out. You can see a real-time barcode, right? Because I'm recording this whole lecture right now. You're probably not doing that. I'm doing this. So now if I go in here and I mouse right and look on properties, there should be a property that enables me to listen to the device. So here it says listen, and you hear this checkbox here? It says listen to the device. Now I'll turn this on briefly right now, and it's going to really screw up my recording. So let's see if it works. Testing. Hello? Apply? This doesn't... Hello? Hello? So now it's stop. Okay. So that's actually a great way to do a microphone preamp. No extra effort needed. Now all you need is an 1/8 inch connector that goes from the earphone output of the laptop into the Arduino audio input, you see. And then once you have that, in theory, you should be able to start to hear the, the audio. So what I will do now, because we've come to an impasse because we're missing certain critical pieces of equipment, is I will stop the recording and then run upstairs. We'll take a little break, and I'll get some more junk. Because obviously we've reached the point where we need more junk. So bear with me.